Okay, so recently I was suggested this integral to do by a friend of mine, and this is from the 2024 Berkeley Math Tournament calculus portion. And I think in particular it's question 7, so if you go on and look for it, you'll find this integral. Okay, now I just wanted to go over something like this because it has a more simpler solution development, more standard, something you'd find in a calculus class. So yeah, might as well start. Okay, so the first thing that you notice is this 5/2 is a weird power, but if you broke this up into 1 plus x to the 1/2 times 1 plus x to the, to the second power, right? Then this is nicer because this and that can now interact, and this is just difference of squares. So we can rewrite this as integral from 0 to 1/2. Right here, 1 minus x times 1 plus x, you just get 1 minus x squared. So if you have taken calculus maybe BC or Calc 2 recently, you'll know where this is going. And I'm going to write this 1/2 power as a square root, just so we can see it better. Then we still have this remaining 1 plus x squared left on the side. So we'll have that there. Then dx on top. And now you see that we have a quadratic here in the form a squared minus x squared. And if you don't remember, then I'll go through this really quickly. If you see a quadratic in this form, and most of the time you use this if it's in a square root or something like that. If you see a quadratic in this form, then the substitution you want to use, the trig substitution you want to use is let x equal to a sine theta or cosine theta. And you can see why, because if you plug in a sine theta into here, you can factor out a squared and you're left with 1 minus sine squared, which is just cosine squared. So right here, we have a equals to 1. So this is 1 squared minus x squared. So our substitution is just going to be x equals to 1 times sine theta. Okay, so now we have to look for our differential element. So take the differential on both sides. Left-hand side, you get dx. Right-hand side, you get cosine theta, and then d theta, like that. Okay, so right here, if you see that with the substitution, if you plug in sine squared, if you plug in sine theta into x, you get 1 minus sine squared, which is just cosine squared. And the square root, it cancels with that square. So this guy right here is really just cosine theta. I hope that was understandable. So that's the point of making the substitution. So let's go ahead and write this out. Now, I'm going to deal with the bounds in a second. Right here, notice that in the bottom, you have a cosine theta. And on top, you have this dx, which is the cosine theta d theta. This cosine right here cancels with that cosine. So all you're left with is d theta. Now in the denominator, you still have 1 plus x. X is sine theta squared. So now, yeah, it looks much better. We can work out the bounds. So when x is 0, so what is theta? Well, when x is 0, we want sine theta. We want sine theta to be equal to 0, right? So theta has to be 0. That's pretty obvious, I'd say, because sine 0 is 0. For the upper bound, we want x equals to 1/2, right? So 1/2 equals sine theta. And for this to happen, I think you could figure out that theta equals pi over 6. Okay, yeah, because sine of pi over 6 gives you 1/2. So we're going to integrate from 0 to pi over 6. So this part took me a little bit to figure out. Right here, you have this 1 plus sine theta squared. And, well, if you just had a 1 plus sine theta in the denominator, your first thought would obviously to be multiply by the conjugate. So I was thinking a bunch of methods. Here, you could also multiply by the conjugate. But because this is squared, the conjugate also has to be squared. So we're going to multiply on the top. We're going to have a 1 minus sine theta squared. And on the bottom, we're going to have a 1 minus sine theta squared. Okay, so these cancel out, leaves you the original 1. You can combine these guys, all right? So 1 plus sine theta times 1 minus sine theta. In the bottom here, what you really just get is this guy times that guy. Difference of squares, you get 1 minus sine squared. Theta, and then all squared. Okay, so the square goes to the outside. This guy is just cosine squared, and cosine squared, squared again, is just cosine to the 4th power of theta. So let's write this out. So the integral is from 0 to pi over 6. Now the bounds, of course, they stay the same. Cosine to the 4th power, that's what we get in the denominator, as we saw earlier. Now, in the numerator, the only real way we can go about this in this particular form is probably just by expanding out the numerator. So I'm going to do that. You get 1 minus 2 times 1 times sine. Okay, so that's just 2 sine. And then plus sine squared. Now you can see that this is nothing but a standard trigonometric integral. Okay, so we can just treat it like one. So it's going to be a little bit tedious, but I think, you know, it's very simple. So let's split this up into 2 parts. Now, if you're doing this for the first time, you're probably just going to split it into 3 and then solve each term, okay? But let me tell you now that this term with the 1 and the term with the sine squared can actually be combined together. So if you wanted to rewrite this, you could get 0 to pi over 6, and then 1 plus sine squared, right, over cosine to the 4th, and then that's the d theta. And then the other term is this middle term right here. So you have minus 2, which I'm going to bring to the outside. Then we have the integral, same bounds. And then we have the sine theta over cosine to the 4th. Sine theta over cosine to the 4th, theta d theta. Okay, great. So now what do we do? Well, right here, we can convert everything to secant and tangent. All right, so this first term right here, we have 1 over cosine to the 4th for the first term, which is just secant to the 4th. Okay. And then the second term, we have sine squared over cosine to the 4th. Now, we can break that up into sine squared over cosine squared. So sine squared over cosine squared is tangent squared. Okay, but we still have 1 over cosine squared. And that is just secant squared, like that. And then write a d theta in. The second term, we can also rewrite. So this is going to have to be smaller, though. Sine theta over cosine theta, we get tangent theta. And then you still have a 1 over cosine cubed, so you get secant cubed theta. D theta. Okay, like this. Now, from here, you can factor out a secant squared, obviously. Yeah, so let's do that. We get 0 to pi over 6. Secant squared gets factored out. And in here, you're left with secant squared. But you can rewrite secant squared in terms of tangent as 1 plus tangent squared. Okay. And then the remaining term, you're left with another plus tangent squared. So I'm going to combine that with this, and then just put a 2 in front. You get 1 plus tangent theta, d theta. And then this guy right here, well, to prepare for the substitution, okay, I should have written a 2 here. To prepare for the substitution, notice that if we just had secant theta times tangent theta, well, the rest would just be a secant squared. So what that means is we could let u equal to secant, right? And then secant theta tangent theta would be our differential element. So we'll rewrite this as such. 0 to pi over 6, we're going to have a secant squared just sitting out here. And then a secant theta tangent theta, d theta. And this right here, once we make the substitution u equals secant, that'll be our differential element. Similarly, right here, once we make the substitution u equals tangent, secant squared theta d theta is going to be our differential element. So let's go ahead and do that. Let u equal to tangent for this one. So I'm going to just do this one first. All right, focus in. U equals to tangent theta. And then du is just secant squared theta, d theta, which we can substrate in. So we get the integral from, well, when theta equals 0, tangent 0 is 0. So the lower bound is still 0. The upper bound, tangent of pi over 6 is just 1 over the square root of 3. So what we get is, well, this secant squared theta d theta is already covered by the du. We have this part, 1 plus 2. Instead of tangent squared, we have u squared. And then we have our du. Okay, and then this is just a game of anti-differentiation. We use reverse power rule. We get, so this 1 gives us a u, and this plus 2u squared gives us a 2 over 3u cubed. And then we have to plug in from 0 to 1 over root 3. When you plug a 0 into a polynomial, only thing that's left is the constant term, but there is no constant term here. So the 0, when you plug it in, it goes to 0, it doesn't matter. You have this 1 over root 3 remaining, so let's plug that in. Right here, if you plug it into u, you just get 1 over root 3. That's pretty obvious. Now, when you plug it into here, you get 2/3, that stays. When you plug in this guy and then cube it, well, you get 1 over root 3 cubed, but you can see this simplifies down to 3 root 3, like this. Okay, these 3's multiply, and then, well, okay, I'm going to bring this over here. So let me copy this down again. These 3's multiply, you get 2 over 9, 1 over root 3. Okay, so this is, well, you can rewrite this as 9 over 9, 1 over root 3, plus 2 over 9, 1 over root 3. That's just, you add the numerators, you get 11 over 9 root 3, which I think is the correct result for this first integral. So this guy right here, all in all, gives us 11 over 9 root 3. So I'll copy this down. And then we can get to work on the second integral. Now the second integral, the u sub is slightly different. Instead of subbing in tangent, we sub in secant. So let u equal to secant theta. And then when you differentiate, you get this secant theta tangent theta out with the d theta. So yeah, now the bounds. When theta is 0, secant of 0 is just 1. And then secant of pi over 6 is, I think, 2 over the square root of 3. So we'll write it like that. All right, the secant right here just becomes a u, and remember it's squared. And then the secant theta tangent theta d theta just becomes our du. All right, great. This is very basic. It gives us, with reverse power rule, 1 over u cubed. Plug in this 2 over root 3 and this 1, and what you get is, I'm going to bring this over here. So 1/3 we can factor out of the two terms, all right? First one, plug it into there, we get 2 over root 3 cubed. And then the second one, plug it into there, which is just 1 cubed, which is just 1. Now this guy right here, 2 cubed is 8, so the numerator becomes 8. Root 3 cubed is 3 root 3 once again. Okay, so 1/3 times that minus 1/3 times that. Yeah, you get, well, when the 1/3 multiplies into this, you get 8 over 9 root 3, because the 3's in the bottom multiply. Subtract off 1/3 times that, minus 1/3, so like that. So that is the result for the second integral. So I'm going to copy that down right here. So the result of this integral is 8 over 9 root 3 minus 1 over 3. Okay, so in summary, well, I mean, we're almost done. It's just this guy minus 2 times that number, okay? So let's write this. We get 11 over 9 root 3. Okay, minus 2 times that. Well, when you multiply 2 by this, you get 2 times 8 is just 16 over 9 root 3. Double negative makes a positive. And then here, 2 times 1/3 is just 2/3. Okay, notice that they have a common denominator. So we just deal with the numerators only. 11 minus 16 is simply negative 5. So all in all, you get negative 5 divided by 9 root 3 plus 2 over 3, like this.